Hello and welcome back to Calculus 1, section 2.6 on continuity. So, the first order of business is to beat down this notion that if you can draw a function in one continuous stroke, it's continuous. There's actually more to that story. But in some essence, yeah, that's true. So this is a that's not a function. There we go. That's a function. The previous one was not a function because, see, it fails vertical line test there. You have to be OCD to be successful in math. So yeah, this line, right, which sits in some xy coordinate system somewhere, is continuous function because it's just one continuous stroke. Sure. So continuous. And say like this, discontinuous. So now, you want certain things to be continuous, otherwise your day would be ruined. For instance, a bridge, right? You want to have a bridge. Oh, that's lost. You want to have a bridge that is continuous, otherwise, right, not good. You also want to have continuous train tracks, right? Subway tracks or something like that. It's important because when those things are not continuous, there you go, right? So as you're looking at the edge of this desk, we call this vertical drop in mathematics jump discontinuity. And you clearly see that this bottle doesn't have a good time as it encounters that discontinuity. Now, if you observe surface from here to here, no problem, right? It's continuous surface. As soon as it goes to the edge, discontinuity kicks in, not fun. This is a mathematical way to describe a cliff, right? So we want to have mathematical way to describe continuous and discontinuous functions because we need them to model the world around us. Now, it's not enough to say, oh, if you can draw in one stroke, it's continuous. Because advanced calculus, right, teaches us, 400 level course, teaches us that there are functions which are continuous, but you have to draw them in pieces. And that, right, breaks this kind of one-stroke definition. So we approach the definition of continuity in a kind of roundabout way. We define continuity at the single point. And then from there, we define global continuity for the entire function. And then discontinuity at the single point. And then with the discontinuous functions, we can define piecewise continuous. So there are these layers that we are going to go through to bring the notion of continuity to the front. So we start by defining continuity at the single point. And then we define global continuity. So let's go. Function f of x is said to be continuous at point x equals a, if, and now we have three conditions that we have to memorize and use. Number one, f of a exists. Number two, limit of f of x as x goes to a exists. And number three, limit of f of x as x goes to a is equal to f of a. This essentially says that 1 is equal to 2, right? The rules. Rule 1 and rule 2 have to have the same answer. So now, if any of the three rules if any of the three rules fail, f of x is discontinuous. At x equals a. So these are kind of two definitions in one. What it means to be continuous at a point and what it means to be discontinuous at a point. Now, the way you guys look at this desk over here, this over here is a single point. If you have your x-axis on the floor, following the edge of the table, going forever, and you have your y-axis going and shooting into the ceiling, well, this line over here is line y equals 3 feet, so y equals 3. And then, as you can see, at certain x value, that y equals 3 becomes y equals 0. And there is the jump discontinuity there. So that's why it's discontinuous at the point. This point here, which is the same as on the floor on x-axis, that's the x equals a at which you have discontinuity. So that's the point that it's important. All other points are perfectly continuous, and we'll talk about piecewise continuity as we move along. So function f of x is said to be continuous at a point x equals a if f of a exists. That's pre-calculus 1, if you can compute the value. Then limit exists, and then finally when those two are equal to each other. Is f of x equals to x squared minus 3 continuous at x equals to, I don't know, 2. I forgot the word is. So is f of x equals x squared minus 3 continuous at x equals to 2? Well, run the three rules. Make sure they apply. This is what I said. Do not play with fire to study examples. All you need to know is the red stuff, because this is for functions in general. I can plug in anything. Exponential, logarithmic, or trigonometric function, or hyperbolic functions you learn in Calc 2. Anything can go for f of x. Don't study examples, study the red stuff. So now, if you study the red definition over here, you know that these three have to hold. If any of these three fail, well, it's discontinuous at the point x equals to 2. So the first rule says that f of 2 must exist. All right, that's 2 squared minus 3, which is 1. Here's your green check mark because number 1 passed. Number 2, we need to figure out that the limit as x goes to 2 of x squared minus 3. Now, there is nothing fishy going on here. There are no denominators to be 0 or square roots to give you imaginary number, square root of a negative, right? So none of the stuff that would create something weird, right, is there. So we can just plug in value and we get 1 again. So it passes on the limit. And finally, number 3, 1 is equal to 1. Passes number 3. So the answer is yes, it is continuous at that point. Now this procedure calculates continuity only at the single point. Let's take a look at another function that we have been beating up to death in this class, and that's 1 over x at x equals 0. So how's the continuity doing? Well, you start with number 1 and you go f of 0 equals to d and e. Done. You don't go on checking other things. As soon as one thing fails, the whole thing is a wrap. Think of your commute to RV. Rule number 1, unlock the car. Rule number 2, drive. Well, start the engine. And rule number 3, drive. You can't really reverse these. You can't start driving and then enter the vehicle. Or maybe you can, I don't know, but I can't. So you start in order because you memorize the definition. If you don't learn this red stuff, well, then don't bother with homework and exams, because such is life, right? You signed up for this, which means you love it. Exactly. I see most of you shaking your heads. No. So all I did is I applied the red. Function value doesn't exist, fails on the first one, done. Discontinuous. I don't have to check rule number 2, rule number 3. The first one failed, move along. How about piecewise function? That is, let's say 3 no coughing for x less than 2, and then x plus 2 for x bigger or equal than 2. Alright, rule number 1. And we are looking for continuity at x equals to 2, obviously, because that's where the break happens. It happens at 2. So what's continuity at 2? Well, we start by figuring out f of 2. Where do I compute f of 2? In x plus 2. Good. Because the equal sign is here. So that's x equals to 2. So I will be computing that here. So that's 2 plus 2, which is 4. It passes the first one. Number 2. Limit of x goes to 2 of f of x. Well, what you have is a line for the approach from the left, and then another line from the approach from the right? So now this actually has to split into two separate limits. The top limit is limit x approaches to 2 from the left side, so minus, and then 3. But we know that the limit of a constant is the constant, so the answer is 3. The other one, limit x approaches 2 plus of x plus 2, is giving you 4. What do we know about this situation? They don't match, which means limit does not exist. Very good. So the overall limit f of x does not exist because these two, approach from the left and approach from the right, are different values. We used the theorem from our first class to come up with this limit. Anytime you have a piecewise function, you have to use that limit, that theorem, which says that the limit from the left and the limit from the right, they have to end up being the same. So it fails on the second rule. Obviously, I will not be checking the third, because as soon as one of the rules checks out, the whole thing is a wrap. So continuity is making the line exactly what the title says, continuous. Any type of open circle, any type of a jump, any type of a vertical asymptote will interrupt that flow, and it will make function discontinuous. One more time, for those of you that missed the experiment, the edge of the desk is discontinuous, because as I walk, like you guys looking at the desk, as I'm walking towards the desk from the right, the limit is 0. If I am to jump up, right, but this is only for 500 pounds, so I can't. If I go onto the desk and I walk on it, right, it is going to be me going to the limit up to the edge, y equals to 3. So you have 0 from this side, 3 from this side, no limit, which means there is discontinuity at the x value along the way. In the world that we live in, that manifests as, right? As a fall. This is the way to mathematically describe a cliff, because there is going to be a jump discontinuity. In this case, it's only 1 foot or 1 mile, right, apart between the y value from the left and the y value from the right. So they are 1 foot or 1 inch or 1 mile apart, and we call that jump discontinuity. We say it's discontinuous because it failed on one of the rules. So now, what are the 3 ways, because there are 3 ways to fail, what are the 3 ways in which the function fails to be continuous at a point? Well, this calls for 3 graphs. And I will ask you to think and help me figure these things out. So all of these graphs are x, y, and I only took the first quadrant. It's enough. So let's say we have this. We have this and this. So let's start with the first picture. All of these this is A, this is A, this is A, and we are considering continuity at A. Well, it doesn't take much of IQ to see that all three of these are discontinuous, right? Because it's not a straight line, a straight shot. What I'm interested in is which rule does it fail as you're looking at the picture. So, how about the first picture? Rule number 1 says f of A exists. Do we have f of A? Yes, very good. So the first one will pass because this over here is your A f of A, where the black dot is. So f of A exists. Therefore, rule number 1 passes. How about number 2? Limit.
No.
Limit does not exist. Very good. Limit from the left is the y value of the black dot. Limit from the right is the y value of the open circle. They are not the same y value. The second rule fails, and that's the reason why it's discontinuous. Well, guess what? This is exactly this problem right here. Jump discontinuity. That's the edge of the desk as the bottle flies off of it. All right, next one. What happened? There is no f of x. Or no, f of A, you mean? Yes. So f of A doesn't exist. Remember the way we compute the f of A. You are supposed to shoot from A, and then when you hit the function, it bounces into the y-axis, right? So that's the way in which we compute. Now consider over here. You shoot from f of A, it passes through this open circle, and it never bounces into y. So it fails on the first. Fails on the first. All right, so let's add the dot. I added the dot. Did I fix it? Well, obviously not, right? If I am to drive on this bridge, I'm still going to go wee through the hole. So, what fails here? Third rule. The black dot is your f of A, so it passes that. So this is where your f of A is, on that elevation, f of A. Rule number 2, limit. Pass, because this is your L. This is where L is. So L exists. Limit from the left, limit from the right, both point to the same y elevation, and the limit exists. The issue is that 1 and 2 are not the same number. Do we all see that? This is where 1 is, and this is where 2 is. Create a snowman. There you go. Perfect. So these are the 3 ways in which function fails to be continuous at the point. Questions? Concerns? Easy, right? Nice. Global continuity. Function f of x is said to be continuous when globally continuous. We have to insert that word. So take the word continuous and move it here and say globally. So function f of x is said to be globally continuous if it is continuous at each of its points. This is global continuity. We have a slight problem here. How many points do you have to check? Infinitely many. Exactly. And then you have to check all three rules. So it's like 3 infinities. Which is highly impractical because we all have expiration date, right? So what do? Well, we write more theorems. The next theorem says following functions are globally continuous. Then there's the list, and that's where your memorization kicks in. Awesome, right? So here we go. Following functions are globally continuous. One, polynomials.
What theorem is their number? Like in the book? Whatever?
Might be.
Oh, okay.
I'll look. So polynomials are globally continuous I'll find it. It's somewhere. Might be all the way. Oh, it's fragmented all over the place. I pull it into one. You will find this theorem in 15 different theorems put together. So, following functions are globally continuous. Polynomials, exponential, logarithmic, radical, rational functions if denominator is different than 0. Number 6, sine x and cosine x, not the other 4. The other 4 have vertical asymptotes everywhere. So polynomials, exponential function, logarithmic function, radical function, rational if the denominator is not 0, and then sine and cosine. That's that. Now, polynomials include constant function, linear, quadratic, and so on. Cubic, quadratic, right? So all of those. That depends on the degree of the leading term. If the degree of the leading term is 2, then you have a quadratic function, which is x squared. All polynomials are continuous. And that's that. I don't care if you have x to the 3750th power, continuous. On its entire domain from negative infinity to positive infinity. Exponential functions again. Logarithmic domain is 0 to infinity, continuous. Radical function as a square root starts at 0, goes to infinity, continuous. Rational function, tricky. So we'll deal with these on the side because changing one sign changes the outcome of the problem drastically. So we have to be very careful with those, which is why I underlined the word if over there. It's not there for decoration. It serves the purpose. And then we have sine x and cosine x. Now this book in its infinite wisdom is also listing tangent x and cotangent x because they're mixing these things on a pile in the book, talking about global continuity and piecewise continuity at the same time. No. We are going to separate these things. So these theorems and definitions that I'm giving are not exactly matching one by one what's in the book. Mathematically it all holds, obviously. And you can always rewind and listen to it again. When I say global continuity, that means from one end of the domain all the way to the other end of the domain, there are no interruptions. Tangent function is interrupted at every n pi over 2. Right? Asymptote at pi over 2, 3 pi over 2, 5 pi over 2. Right? Tangent function has infinitely many vertical asymptotes. That's infinitely many discontinuities. And yet it made to the list of continuous functions. So definitions matter. Definitions matter. The book is talking about piecewise continuity right away. What they do is they chop off just the principal domain of tangent, which is from negative pi over 2 to pi over 2, and they say, yep, continuous. Right? So we have to be careful about those things. We discussed last time, you do not want to design something that will have a vertical asymptote in the middle of whatever your power source is. Right? So sine and cosine, they are the two trig functions that do not have vertical asymptotes. So we list them here. The rest of them will add. Yes, the rest of the functions are going to join the gang, but we have to first talk about piecewise continuity and other things. Before we get there, though, another very important theorem which states that combinations and compositions of continuous functions are continuous. This one is going to be written in blood. Combinations and compositions of continuous functions are continuous. Combinations and compositions of continuous functions are continuous. This means that addition of two continuous functions gives you continuous function. Just think about it a little bit. X squared, continuous, plus 3x, linear function, continuous. All on a pile, it's still quadratic, continuous, right? As simple as that. F minus g, f times g, f divided by g provided g can't be 0. That's the rational part we talked about. F raised to the n. Guys, this includes not just squares and cubes, it also includes all of your square roots and cube roots and so on. Anytime in calculus and beyond, when you see f to the n, be nice. Don't discriminate against fractions. All right? If I say f squared, we know f times f. But if I say f to the 1/2, that's a root f. It's exponent. It's a number. Be nice. Are we all green? Good. So when I say f to the n, that doesn't mean just f squared. It also means square root of f and cube root of f and all the others. So we have addition, subtraction, multiplication, division, making sure g is not 0, and then we have the squaring. Now we have function composition, so we're going to write, some of you are used to f composed with g, some of you are used to f of g, whatever, and then the other way around, g composed with f, which is g of f of x. So, here are your combinations and composition of functions. Anytime you get any of the functions that are combined in this way, they will be continuous at the end. So an example is no coffee. E to the sine squared x continuous. And you say, yeah, because all of the functions that are involved in function composition are continuous functions. Now, this is the part where you have to know your pre-calculus 1 or you are doomed. How do we decompose function composition of this kind? Well, we have definitely e to the x on the top. Dig one layer down, what do we run into? Very good. And then dig one deeper, what do we get? Oh no, sorry, that's not sine x, it's x squared. And then sine x. There we go. Much better. So how do we put this together? Check. Sine x gets placed into x squared to create sine squared x, which is placed into e to the x to create e to the sine squared x. Snake behind, right? Like layers of the onion. Layers of the onion. What is on the surface of the onion? It's e to the x, right? If you are to stand far away where this exponent just blurs into a blur, all you see is e to the x. That's your outer shell of the onion. That's the main function, the f of x. We are going to do this decomposition to the point you're going to get sick in this class, because the most important and most used derivative rule, called chain rule, depends on this type of calculation, of decomposition. So, you need to know this. So, e to the x is the outer shell. Then you see the exponent, forget about that anymore, right? Now you're just staring at sine squared. Sine squared x can be rewritten as sine x in parentheses everything squared, which is the reason why you get the x squared to be the next level. Because it's just x squared. And then in that x is actually sine x. So sine x is the core of the onion, in the middle. Sine x gets placed for x here, becomes sine squared x, and then the whole thing gets placed into x to give you the function. What I have done, I have decomposed function composition and came up with three functions that by blue theorem are all globally continuous. The red theorem says composition of continuous functions is continuous. Well, guess what? I got three functions that are continuous. Therefore, yes. Function composition of continuous functions is a continuous function. You're looking at this maybe and saying, I just need to solve that one problem on the test. Right? No. How about some time travel? We paid for the class, so why not do the time travel when we can? I will take you to the future. Calc2. This is called integral test. You don't have to understand anything. The theorem for the integral test has words, and then it says three conditions have to check off before you are allowed to use integral test. Condition number one, continuity. That means that the problem we just did in Calc 1 is going to be solved in a margin of the problem as a setup for a Calc 2 problem. So, when I hit the problem, this one, doesn't matter what's happening in a problem. I want you to focus on number one. It says, is it continuous? What? Well, this function, is it continuous? And we say yes, because both 1, that's the constant function, and x squared, parabola, are both continuous. That is your blue theorem. And their quotient is continuous. In the red theorem, you have f divided by g as long as g is not 0. Now, you would say, hold on, x can be 0. No, because our domain from 2 to infinity, so our domain is 2 to infinity, 0 is not in a domain, discontinuity is not in a domain, boom, continuous. See that? That's how you play the game in Calc 2. Next problem. P series, keep moving. Back to integral test, right? Problem 23 from homework from textbook. It says what? Is the function 1 over square root of x plus 8 continuous? Yes. Why? Because the only number that would make denominator 0 and ruin our day is negative 8. Negative 8 is not in the domain. This is polynomial. This is function composition of a polynomial and a radical. You see, the blue and red, they take care of 100% of situations. You just have to play the game of the domain and make sure that the bad points are not part of the domain, which they're not. So, by using all the Calc1 theorems, right? That's a constant, that's a polynomial inside the square root. We know that f to the n is continuous, function composition is continuous, so that makes the square root of x plus 8 continuous. And now division as long as denominator cannot be 0. What makes denominator 0? Negative 8. Well, negative 8 not part of the domain, kick it out, bye-bye, and we have continuous function. That is done as a setup. What is the integral test? This is the integral test. This over here is preliminary work in Calc 2 to make sure that you are allowed to do this. So this lecture is not something that you pass for the exam. You have to know this stuff, or you will have to relearn it when on top of something that you were supposed to know from Calc 1, you actually have to learn your Calc 2. And then you have the conclusions from Calc 2 and all of those things that are coming up. Do not study for the grade. Your grade is completely irrelevant. Right? It could be the measure of your achievement. It's not the measure of your intellect. If you want to know if you're smart or stupid, I told you, take the IQ test. Math exam has nothing to do with it. You will study the red and blue, and you will do well, or you will try to study examples and fail miserably. It's a very simple thing, and I understand it's very hard to shake that off because so far over. You have to know the red and you have to know the blue, because my example with e to the sine squared and this problem here have nothing to do with each other, right? Yet they were solved with the same red and blue statement. So that's where you study, and the grades and everything else will follow. Forget about the examples. Study the theory, and then when you have the tools, when you have the right tools, you get to do the stuff properly. So let's go back to our Calculus 1 class, back to our example, and realize that decomposing a function, which is pre-Calculus 1, into 3 functions. Okay, all of these 3 functions are on our blue list. Yay. Function composition is on the red list. Yay. Put that all together, and this whatever it is function is continuous. And now you can go and you can plug that in Mathematica, and you will see a line. Whatever that line does, I don't know what it does, but it does something. And you will be able to see no vertical asymptotes, no open circles, because none of the functions allowed for it. Now, we could have a function that would ruin your day, like 1 over x, where 0 is allowed. It's not excluded in the domain, like in those Calc 2 problems. So if you run into that, well, you got the discontinuous function. It's okay, right? Your job as engineer is to patch the hole. But you need to know where the hole is, and you compute that, right? So that's your discontinuity. So now, as we are looking at this, it is time to talk about piecewise continuity and then close the loop with the book, right? Is tangent continuous? Globally, Hell no. But there are pieces that are continuous, which is fine. You've seen me in Calc 2 use the piece of the function rather than an entire function, because the problem was defined on a piece, and that piece happened to be continuous. Yay! There are more of those things happening in Calculus 2. I can jump into another section on improper integration, where you have a vertical asymptote in the middle of your problem. If you don't see it, if you don't know it, your answer is garbage, right? Because you will get a nice finite 2, yet the answer is infinity, right? So these are the things that you have to be very careful with, and continuity is going to define a lot of those things later on. So, piecewise continuity. Simply, your function is in pieces, and then each piece is continuous on, certain interval, and you're done. So let's take a look at the most used and abused function, 1 over x. As I draw the function here, continuous or discontinuous? Discontinuous. There's there at 0. So 1 over x is discontinuous at x equals 0. However, it has 2 piecewise continuous parts. Negative infinity to 0 and 0 to infinity. So maybe I just need to use half of the function, and if I only need to use half of the function, great, it's continuous. So this is how the tangent gets to be continuous. We know it's discontinuous. But if you chop it up from negative pi over 2 to pi over 2, that one squiggle is going to be continuous. And that's that. So now, as another example, y equals tangent x. And if I draw these vertical asymptotes and I hit the function through, that's continuous, right? But it's piecewise continuous. Only the piece between a negative pi over 2 to pi over 2 is the continuous piece. Then you have the next continuous piece from pi over 2 to 3 pi over 2. And, as I said, every odd pi every odd pi over 2 will have the vertical asymptote and another continuous piece trapped within. Let me just put this in just in case. Note that y equals tangent inverse of x is globally continuous because it looks like this. This thing shoots to positive infinity and negative infinity. So no vertical asymptotes, no open circles. This is the function that you have to memorize because it's going to pop up in Calc 1, Calc 2 differential equations. So I know I said this already, that this function is important, but I just need to make sure that you know it's important, because it will pop up. Good. Yes.
Does that also work for the other piecewise functions that we did originally?
Well, this is not piecewise function. The inverse tangent is not piecewise, right? It's globally. Oh, anything. Yeah. Anything that has vertical asymptotes, you can chop it up, right? And each piece is continuous piece. So I believe I had, when I talked about vertical asymptote, yeah, this one, right? We talked about this. This is discontinuous, right? It has two vertical asymptotes. It's discontinuous. However, it has three pieces, and each piece is continuous piece. So from negative infinity to the first asymptote, and then between two asymptotes, and after the second asymptote, each one of those pieces is continuous.
What if there's a hole at a certain point? Is it the same?
You are going to make another break there, because it's discontinuous at the hole, right? That's, you know, it's the hole in a path. This calls for an example. Look at that. It's discontinuity right there. That's your open circle, right? Now I can't get it. I didn't think this through. Wow. I took care of exercise for this week. That's good. All right. That's continuity. I hope you're not disappointed. Right? Continuous at the point, discontinuous at the point. Then we take all of those points, create global continuity. Then in the globally continuous function, right, we have vertical asymptotes and open circles and all of those things. And then we define piecewise continuous. What I'm asking you to do is to learn the reds and the blues and all of these things that I'm using different color, because those are your tools to solve problems. Sure, you're going to look at examples, but do not study and memorize examples. Because when you memorize x cubed and I put x to the 1/3, you go, oh, because that's now, what is the graph of cube root of, right? What is the graph of cube root of x? Go ahead. Okay. Glad we have this talk, right? Looks like this. I don't. So, one more concept left, and that's intermediate value theorem, which utilizes the concept of continuity. It's like the application, right? Everything that we create and machine and whatever, or when you look at economics and stuff like that, has as a base mathematical equation. So intermediate value theorem is actually a way to solve any equation out there. Now, that is extremely important. If we are not solving equations, we are not having mathematical models, we are not modeling the world, we are not understanding the world. Then we go back in time and bang rocks to make fire, right? That's very simple. So, intermediate value theorem in its core appearance doesn't look like anything important or so on, and certainly we won't bother with it because we don't solve equations that way. But you have to understand that this is the core of everything that our civilization has, because it is equation. And solving the equation is important in every aspect of our existence, right? For any kind of discipline or so, you always have some kind of equation to solve somewhere. So let's go through the theorem, and then we're going to actually tie it to equations and see in which way this solves equations. So it says, suppose that, so red, suppose that f of x is continuous on interval a, b, which is closed interval a, b, which means includes the endpoints, and L is a number strictly between f of a and f of b. Then there exists at least one number c in AB such that f of c equals L. And then we have a graph that goes with it. This is our f of x. This is my a and f of a. And this is my b and f of b. Then finally, this is my L and C. Suppose that function is continuous. We see it, right? And it's continuous on interval between A and B, including the endpoints. And then those A and B give rise to f of A and f of B. So now we say let number L be strictly in between f of A and f of B. So it's somewhere in between. Anywhere. The last sentence says that that L is produced by some value C, because the function was continuous. L is trapped between y values of A and B, so there has to be an x value that makes that L. At least one of them. You can have more, but at least one. So how is this important? Well, it's important if you shift the function down to the point where L collides with the x-axis. So the answer is 0. So if you do that, you are going to run into a problem that now has A, f of A, and B, f of B. The value on the x-axis, because your L is 0, is C. Any equation equaling 0 follows the situation and the solution is x equals c. Without a fail. Now you can always make equation equal 0 because you can move all of the stuff that it's on the right to the left by adding, subtracting, multiplying, whatever witchcraft you can pull off, and you get 0 on the right-hand side. The solution to that equation is going to be c. Now the coolest part about this is that you can actually, if you have time and patience and will, you can calculate that answer to any decimal precision that you want. Way beyond your 12 digits on a calculator or 150 digits on a computer or whatever. If you want to sit there for 10 years and compute these decimals, 8 hours each day, you have thousands of decimals calculated. The trick is, if you notice, if your interval a and b is around, trapping the solution c, your f of a and f of b always have a different sign, the y values. See that one will always have to be below and one will always have to be above x-axis. The other situation that you might encounter, right, would be this one. So here's your a, with f of a being on top, but then your b is now on the bottom. See that? So what do? You make the educated guess of where your answer is. Let's say it's between 1 and 2. And then you check those endpoints in a function. If one is positive and the other one is negative, solution is guaranteed between 1 and 2. And then you make another guess. You move 1 to 1.5, or you move 2 to 1.5, whatever. Move either one. Compute at the endpoints again. If they have opposite signs, your new smaller interval trapped the solution. Keep cutting and refining and refining and refining. You can go to any decimal place you want. I'm not sure if I did this calculation to show it off in one of the classes. Let me try go hunt for it. How about this one? Continuity. Right on money. I came up with the equation x squared minus 3 is equal to 0. We know the answer is square root of 3, but we don't know exactly how much that is in a decimal form. So what do? Well, I know that the answer is between 1 and 2, because square root of 3 must be between 1 and 2. Square root of 1 is 1, square root of 4 is 2, square root of 3 is in between. Common sense, right? So, my initial guess is interval 1 and 2. I compute that function at endpoints, and I get -2, -1. This means the answer that I'm looking for is between 1 and 2. Look at me start off writing that answer, 1 point. See that? Now, I say, let me make the further guess. I'm going to change my 1-2 interval to 1 and 1.5. I already have the first number in my answer, because if I know that answer is trapped between 1 and 2 because I got positive and negative, I know that the answer is trapped between 1 and 2, obviously answer has to start with 1 point something, right? Because I have 1 to 2 and now I want to see whether if I do 1 and 1.5, where I'm going to do well. I shouldn't, right? Well, yeah. You see that? Calculated f of 1, calculated f of 1.5, they're both negative. And I need positive and negative. Because only when you have a positive and a negative, it guarantees that the answer is trapped in between. I got both negatives. So, the answer is not in this interval? Well, if it's not there, then it must be between 1, 5, and 2. Great. Now, so we are good for 1.5 to 2. So what I'm going to do is I'm going to chop that 1.5 to 2 in half. So 175, 2. And I ask students to pick these numbers. So now, students picked 175 to 2. And we got 2 positive numbers. Bad. That means that the answer is not in 1.75 to 2. That means it has to be in 1.5 to 1.75. Great. That was the next step anyway. So answer must be here. So I chopped that. And we went to 1.7 to 1.75. Guess what? 1.7 to 1.75. I had the positive and negative. I got the next digit. Because all of the numbers that are between 1.7 and 1.75 are starting with 1.7. Common sense, right? So we just got another digit. You can continue this until you bleed under your fingernails, and you will have thousands of these digits. You keep playing this game. Just the basic calculations. We don't do any fancy math here. You are plugging in these numbers that you are chopping, the interval that you are making smaller. You are plugging those in equation that you have at the top of the book, on top of the problem, and you keep going, you keep going, you keep going. 1.73, and then I got bored and we just quit. At this point, we already burned like 30 minutes on doing this. So obviously, this is amazing. If you have nothing else to do, please, by all means, don't be bored. You can figure out a lot of awesome stuff by calculating this. So, so that's that. That's your that's the intermediate value calculation. And as you can see, the C is the solution that you're looking for. As you are cutting the interval into smaller and smaller parts, you are zooming onto this one. Eventually, you are going to start hitting digits that will give the tens and then hundreds and then thousands and 10,000s and keep going to any precision you want. There are no limits to how far you can get.
Are the answers to the 40 positive or negative of the function process the x-axis?
Well, those are the y values, right? So as you can see, negative and positive, and then negative and then positive.
I'm saying, like, what if it's the first case where the function
because you have A and B as bounds, it chops it up, right? Now, can this method fail? Yes, if you're not careful, it can fail, because you can have a parabola that cuts two solutions, and you pick your A and B in such a way that they both return positive values, and you might conclude that there is no solution in that interval. Wrong, 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 right? So don't take your intervals to be, you know, huge. One unit somewhere, and then you start. One problem on your lab will address this calculation. Play a little bit on the calculator, and you will be able to guess the intervals on which you have these solutions. Yes? Me? Of course I can. I should. It takes forever. We can try it on Thursday, or whatever the review is. But again, that calculation is not. the reason why it's not something that we practice is because we have calculators. We don't have to do these things. Second, we have much better way to solve equation. This is just like the guaranteed way. You know, when you don't know how to graph a function and you go back to the middle school, pick x's, calculate y's, connect the dots, right? Like in a coloring book. That's that, technically, right? Which is the reason why we learn, so we don't have to do it. You know how to solve quadratic equations using the formula, how to solve linear by moving stuff, square root function to square both sides, exponential function to log both sides, right? Which is why we don't do this. We learn, you spent 3-4 years of math learning how to solve those equations, and now you want to go back to Stone Age, right? So that's that part. Which reminds me of solving equations in general. Now that you're in calculus and that much of your previous education was absolutely stellar, probably we have some shining examples of good education, actually. When I started tutoring at math, I learned a very disturbing truth, and that is that in this country no one teaches graphical solutions of the equations, which is actually the way to go. So if I am to ask you x plus 3 equals 5, everyone is going to say, do what? Subtract 3 and answer is 2, right? Yeah, that's true. But I'm going to now switch this and say x plus 3 equals e to the x. Now what? Do the log, right? So we ln both sides. That's gonna kill DC. And now you have ln of x plus 3 equals x. Now what? I think I heard it over there somewhere, e both sides, to kill the log. Sure. E both sides to kill the log. And we have x plus 3 equals e to the x. That looks familiar. This is algebraic way attempt to solve the equation. Let me give you the answer to it. You know what this is?
A teardrop?
It's a tear, yeah. It cannot be done, no matter what you want to do. Algebra cannot solve this equation. Nothing. You can just sit there and weep, and that's it. So this equation cannot be solved by algebra. So what is that ultimate powerful way to solve it? Well, sure, this will work anytime, but it's annoying. So let's solve equations in a different way. You see, what you have anytime you have an equation is you have equation on the left and equation on the right as a functions. When you graph them, they either intersect or they do not intersect. If they intersect, that's your solution. If they do not intersect, there is no solution. And that is the ultimate way. So let's solve our first example. I know you all went in your head minus 3, x equals 2, and yeah. But look at this. On the left-hand side, I have a linear function. You'll catch up. Just look. Y equals x plus 3. On the right-hand side, you have a constant function, y equals 5. When you say y equals y, you do get x plus 3 equals to 5. Bueno? This point over here is called the point of intersection. What is its x value? 2. Exactly. That is how you solve every possible problem ever. Now, yes, you can do minus 3 and minus 3. And it is faster to do minus 3 and minus 3. Is there a minus 3 that you can do over here? No. Right? So now you are stuck with the only method which works. And that is your algebra. Graphing. X plus 3 and exponential e to the x. I discovered by this graph that I have x equals x1 solution and x equals x2 solutions. This is going to spit out 2 solutions. Now, where are those solutions? That depends on the level of your OCD to draw this perfectly, which you cannot do on your garbage-lined paper. You need a square grid, and you need the ruler and all of those things to have them, and then you can approximate. That is going to get you in the neighborhood of the answer, and then you unleash this beast, and it just rips it apart. It gets you to any decimal precision you want. You need 100 decimals? Stick around for a year, you got it. All right? Had those calculations. So that is how we solve equations. You are also going to encounter equations that are quickly solved, like sine 2x is equal to 1/2, right? So what do? Well, sine 2x, this 2 is going to make the sine faster, which means that when you draw your sine function, I'm going to put these points. Since 2x, so 2x, that makes it faster. That means it's going to be pi over here and pi over 2 and pi over 4 and 3 pi over 4. All I did is now I graphed the left side. I'm going to graph the right side. So on 0 to pi, 2 solutions. One over here, one over here. I mean, they're x values, obviously. It's called the boss way of solving these things. And again, you are not supposed to get the 8th decimal off of the graph that you did. You just need to know that the answer is about 1.5, and then you are going to do the rest with this thing. Now, clearly, all of this is irrelevant because you have the calculator and Mathematica and satellites and things to to do these calculations for you. But I can paint you the picture of, you know, the desert island, the battery in cell phone is dead, the battery in calculator is dead. You need to make the shelter. You need the square root of 3. The Wilson is gone. What are you going to do? Stick, sand, and you got it. Right? Because you can. See? It's what it is. Can't make a hut without knowing the square root of 3. I mean, or ln 3. Oh, that's it. I'm just going to say bye.